So one more property. So you see this beginning here is a little bit dry because it's a lot of definition of convex function and convex set. But I'm trying to go a little bit, giving really the essence of what you need. Because if you read Stephen Boyd's book, you will read 100 pages of just properties of convex set and convex function, and you will easily get lost into how this is actually used in communication. So one more property that is useful of convex function is two more properties here. Is what happens if you sum two convex function or n convex function. And the interesting thing is that if you have a non-negative weighted sum, so I take, for instance, two convex function f1, and I sum with another convex function f2, this would be a non-negative weighted sum where my weight are 1 and 1. Essentially, this will be still a convex function. If you take the difference of two convex functions, this will not be convex. So if I do f1 minus f2, and f1 and f2 are convex, this is not convex in general, right? So it has to be a non-negative weighted sum of two. So you can have alpha multiplied by beta, but alpha and beta have to be positive. And so, for instance, I mentioned earlier that if you do x log x, this is convex, right? How would you show that? You can take the second order derivative with respect to x and show that actually this is positive. So this is convex in xi. If I now sum over different value of different variables, so over different xi, so this will be convex as well, right? So this is interesting because there are multiple ways of finding whether a function is convex. Either you apply the original definition, or you take this first order condition, or you take the Hessian, or you say you're using some properties. And this is one of the useful properties that say, well, if I have two convex functions, I've summed them up, it's still convex, right? And another useful properties is this one. It says, well, if I have m convex function, f1 to fm, and I take the pointwise maximum of those m. So for any values of x, I take essentially the value of my function will be the maximum between f1 of x to fm of x, right? So for instance here, so this pointwise maximum is still convex as long as the underlying function f1 and fm are convex. So this is an example. I have two functions that are convex, right? You can see from the line segments is always above the functions, or actually you can see from the curvature. And if I do pointwise maximum, that means I take any x value here, and for these values of x, I have f1 of x and f2 of x, and I take the maximum between those 2 points. And so what will be the maximum? It will be essentially this, then this, then this. And this will still be convex, right? And the opposite, if you do the pointwise minimum of concave functions, you're going to have a concave. So here I have two concave functions. You see the curvature is negative. And what will be the pointwise minimum? It will be here, f1, and then I switch to f2, and then f1, and this will be concave. Okay, so this is also a useful property. Right, so now let's come back to our optimization problem, and we say, well, I have this optimization problem, and I wonder when is this optimization problem convex? Well, it's convex if you have multiple things. The first thing is that your objective function has to be convex. The second thing is that your inequality constraint here have to be convex. And the third one is that your equality constraint here have to be affine. So they have to be some form of linear plus a constant. Total a constraint. But this is a affine constraint. So you cannot have a quadratic equality constraint, for instance. It has to be affine. This has to be convex, and this has to be convex. That would be the definition of a convex problem. And the interesting bit is the following one. So here, if this is convex, and I have m of them, this is like saying I have essentially each of those convex inequality would give me, if you think about what we had, for instance, for the half space, where you had multiple of those half space and the intersection. Here I have the intersections of the m inequality constraints, and this is equivalent to saying that those m inequality constraints will actually create the intersections of m convex sets, which actually will appear convex. So you can view this constraint here as saying equivalently, I'm minimizing a convex functions over a convex set. And so, for instance, if I take here my f of x would be my half space, for instance, right? And I have this kind of constraint. So each of those f of x, fi of x is a half space constraint, for instance. I would have an intersections of those half space, and that would create a convex set. And I would minimize a convex functions over a convex set, right? So that's an equivalent way of saying what is a convex problem. So either you minimize a convex function over a convex set, or you say you minimize a convex functions over convex inequality constraints and affine equality constraints, right? Those are two equivalent formulations. Right. And so I told you at the beginning, one of the very interesting property of convex problem is that they have a global optimal solution. And this is what you see here. The property is that if you have any local optimal solutions of your convex problems, this local optimal solution will be a global optimal solution. So this is very powerful result. So imagine you have a value of x that is here, and your value of f of x is given by this point, and you say, let's look around this area. And let's find whether this x, this point here, is actually local optimum. So it would be local optimum if I cannot find any points nearby whose values of f of x is smaller. But here you can find a value. If I take the value of z, f of z is actually smaller than f of x, right? So here clearly this point is not local optimum. But if I come here, I can search locally, and find that locally, well, this point is actually the local optimum. If I move to the left or I move to the right, the function f of y will actually increase, right? So this is a local optimum point. Well, a convex problem, the usefulness is that if you can find such a point that is locally optimum, you can say, well, this local optimum will be global optimum. So you don't need even to have to search over the entire space. If you can show that just you have one local optimum, and around that locally, around that point, this is indeed local optimum, then you can conclude that I don't need to search over all the domain. I know that this local optimal will be global optimum. So this is a very powerful result. So even if you were searching everywhere in the domain, you would not find anything better. And this is really the property of a convex function, because if you have something that is non-convex, you cannot say that. And you can see this quite easily with an example, right? If I have a function that is something like this, right? This is clearly non-convex. And if I have a local optimum here, well, it's local optimum. If I move to the left, I move to the right, I see that actually this point is local optimum. But I cannot conclude that this local optimum is global optimum, right? While if the function was convex, and I have something, for instance, like this, right? If I find this point that is local optimum here, I can say, okay, I'm sure that now this actually will be the global optimum solution. Right, so now let's look at various type of convex problems. And so this is the first one, linear program. This has been used for a very long time. Unfortunately, it's not so much used in wireless communication, and I don't think Hongyu has used this in wireless communication. Actually, I have never used this in wireless communication. But essentially, it says the following. It says you have an objective function that is affine, so linear plus a constant, and then you have your constraint here. They're essentially also all linear. So you have linear inequality, so you have a matrix inequality equality here. And this term here, this essentially says that this is a matrix, and these curly curves here, do not get confused with the positive semi-definite. What that means is essentially g of x smaller than what I write h here. I have multiple entries here. This is a vector. This is a matrix, right? So this is equivalent to saying I have, I don't know, G1, the first row multiplied by x is smaller than H1. The second row multiplied by x is smaller than H2. The nth row multiplied by x is smaller than Hn, right? So you have essentially n inequality here that is written within this compact form. Right, so this is sometimes called element-wise inequality. So the key is that you have different formulation. Some people write it like this, you can write it like this, you can write it like this, but essentially you have linear objective functions, and you have here linear inequalities. So everything is linear. Right, and so this is an example, for instance, of linear inequalities. What is this? This is your polyhedron, and your polyhedron would be obtained, for instance, from those sets of n inequalities here. So each of them, again, if you think about this, this is like a half space. Each of them defines a half space. This is another half space, so this is an intersection of n half space. And this is what I have here. I have an intersection of n half space that creates essentially my feasible set. So the solution to my problem has to be searched over this domain P here. That is a physical illustration of, for instance, this set of constraints here. And what I want to do, I want to minimize, for instance, this linear function here. And that says the following. This is those lines are the level curves. So it says those lines are the curves for which the objective function is constant. So this is the value of c of x, c multiplied by x. This is my objective function. So this is my objective function, c of x, and I'm looking at different values of c of x, right? C of x, sorry. C multiplied by x. So I'm looking at CTX is equal to 1, CTX is equal to 2, CTX is equal to 3. And what I want to find is the value of x that leads to the smallest objective function while still being within this polyhedron. And so, for instance, here, this would be C multiplied by x equal to 5, equal to 4, equal to 3, equal to 2. And so you're looking at the point that belongs here, but whose level curve is actually the smallest one, right? And what does that mean? If you remember, I guess you have all learned about gradient. What is a gradient is directions where your functions increase the fastest, right? So if you have a ball, for instance, at a certain point, and you compute your gradient, you will see the directions where your function increases the fastest. So if you think about this, you want to run in the other directions if you want to minimize your function. So you don't want to look at where your gradient is the largest. You want to look at that directions, but the exact opposite. So this is where your function will decrease the fastest, right? And this is what you have here, essentially. This these directions will be where your function increases the fastest. These directions is the functions where your functions will decrease the fastest. If your objective function is c multiplied by x, your gradient will be vector c, and so you're looking at the opposite direction, so that's why you have the minus c, right? And so you're looking at the directions where the opposite direction to your gradient, but still you find a point that is still within your polyhedron. You cannot find a point that is outside because then it would not be feasible, it will not be within your constraints. Okay? So this is a visual representation. So here's another example. So I have these linear objective functions. I have a linear equality constraints. And I have here that my points x1 and x2, they have to be in this non-negative orthon here. So they have to be for x1 positive and x2 positive. And so what you do, you want to look at this constraint here, which is on this line. You want to look at within this quadrant here because you have to be positive. So your point objective value has to be on this line segment here in order to satisfy the constraint. And what you do is that you look at your objective functions and you minimize it till you leave the this feasible set. So your feasible set is here, and as long as you touch it, you find a point on this line is okay, you're going to find a feasible point, and once you leave it, you lose it. So here you see that this point will be the optimal, is where your level set is the smallest one, and you're still on this line segment. Okay? Right, so this was linear program, very interesting, used a lot in practice, but not in communication. Or as far as I know so far. Okay, so what is more interesting is those QCQP problems. So this is problems where you can have quadratic objective function and potentially quadratic constraints. So this is an example of a quadratic program. So you have the affine part, so that's your constant, the linear part, and this is your really quadratic part. And here you have constraints that are still linear inequalities and linear equalities. So this would be a quadratic objective functions, but with linear inequalities. And remember, this problem will be convex if the Hessian of that objective function, this is fine, this is convex. This will be convex if the Hessian of this is convex, and to be convex, your P has to be PSD, right? So this would be a convex quadratic program if P is actually a positive semi-definite matrix. And so what that means is that what is this set is again this polyhedron, is this intersection of half spaces. So I have something like that again. So I still have a constraint or a convex set here that is this intersection of half space. But now my objective function is not linear anymore. So it's not those kind of level set that are lines. It's quadratic. So quadratic, what that means is that this shape will now look like an ellipsoid, right? And it's an ellipsoid, especially when this P have non-equal eigenvalues. This is clearly an ellipsoid, so it pushes in one direction more than other directions. So one example of that is the following one here. I still have my polyhedron that defines my convex constraint set, and I'm looking at now a function, an objective function that is not linear, is quadratic, so that creates those levels here. They're not lines simply, but actually are ellipse. And you're looking at the point within, or this feasible point, that is such that you minimize the function, the objective function f0. And so what you do is that you imagine this, this polyhedron, And those level curves is like a ball. It's literally like a ball. Maybe you pull this ball into more in one direction than another directions, but it has this shape, right? And what you're doing, you compute your gradient, and your gradient, you're trying to shoot in the opposite directions to your gradients. So you try to really shoot where, not when you increase the fastest, but the exact opposite. And that will give you the points, directions where actually you're going to find your minimum. So here you're going to have high level curves, and then as you go towards that directions, you're going to have lower level curves. And so this point is the one where essentially you minimize this objective function because you actually on a level curve that is the smallest one, and at the same time you belong to your polyhedron, which is your constraint set. Right, and so if you have a quadratic program, but this also quadratically constraints, so instead of having now those linear inequalities, now you have also a term here that capture the quadratic aspect of the constraint, and you can have also linear equalities, but the important bit here to have this QCQP is that you have these quadratic constraints and quadratic objective functions. And this is, again, convex if both P0 and Pi for all those constraints, all of them are positive semi-definite, right? So the Hessian of all those functions has to be positive. And so what that means here is that you still have an objective function that looks like an ellipsoid. So the levels will look like ellipsoid, but your constraint set here will be an intersections not of half space, but will be an intersections of ellipsoid as well. Because each of them will actually define an ellipsoid, right? Good. So a linear program is a particular set of a quadratic program which is itself a particular instance of a QCQP. So where do you have LP from this? You have LP if you turn off this term, P0 is 0, Pi is equal to 0, so you end up with only this part. This will be the linear program. QP is when you turn off Pi, so you have an objective function that is quadratic, and you had the constraint that actually linear, and then you have the QCQP when P0 and Pi are non-zero. Right, and this leads to our first example in communication. So this is now a problem that is very relevant for this scenario here. This is transmit beamforming in the unicast scenario. So I'm transmitting independent streams to different users, and I want to satisfy a certain quality of service at each of those users. And how do I write quality of service? It means the SINR for each of those receivers has to be larger than a certain threshold. This is what we define by quality of service. And given those constraints, I want to minimize the power. Right? So what does that mean mathematically? It means that I have K precoders, 1 precoders per user. The norm of W, and you have to be careful here, those W is what I was calling P in part 3, right? So those are not only the directions of the precoders, they also capture the power location, okay? So this essentially, the norm square of W means the power that is allocated to stream I, for the second stream, for instance. And I'm summing over all of them. So this is the total power that would be allocated to this system at the transmission. And now I'm subject to an SINR constraint. I have my intended signal power, and I have the interference created by the beam or the precoder J to user I, for instance. And this SINR for user I has to be larger than certain threshold sigma I or gamma I, right? And this for all for all I. So I have k users. Each of the users will have to satisfy a sign R constraint like this, and I want to minimize this power. Okay, so this is an example of problems, and how can we write this equivalently, and whether is this a convex problems or not. So one way of rewriting this is the following. Norm square of W, you know this already. This is nothing else than W Hermitian W. So I'm not changing much here. But now I'm writing this inequality in a different way. I take this term here, I shift it to the left, and I bring it back to everything to the right side. So now I have this term here, which is nothing else than this term, but expanded. Right? This is a scalar. So it's a scalar multiplied by its Hermitian. Essentially, I have essentially this is nothing else than this, right? And in this case, HW like this is like HW, W Hermitian, H Hermitian, right? That's the same thing. And so what we have here is this term is this numerator, and then we have this term here is this denominator there. Okay, so this is getting a little bit more complicated because here we have a quadratic function. I have precorders I on both sides here, and I have here effectively a matrix that is positive semi-definite, right? With non-zero eigenvalues, but one of them will be positive, right? So this is PSD. So this is a convex function. And here I have something similar. This is also a convex function. And you remember sum of two convex function is convex. But here I don't have a sum, I have a difference, right? So I have a difference of two convex function, and this is something that we don't like. This is typically non-convex, right? So, so when you look at this formulation, you will say, well, this will not have a global optimal solution, so I don't know how to solve that. But it turns out that this has a very useful, very specific properties, and we can transform this into another form that will appear actually convex, right? So that's why I was saying at the beginning, the way you formulate the problem is very important. It may appear non-convex at first, but you can transform sometimes into a form that is convex, and actually then you can really solve using state-of-the-art tools. Right. So, so let's look at that using different methods. And the first method we're going to look at after this QCQP is this, the problem of SOCP. So SOCP is second order cone program. And this is a kind of generalization of QCQP. And what I will do, I will present SOCP and then some other method, and then we will come back to this problem, and I will show you how you can actually solve this problem using those SOCP and other methods. Right. So SOCP is slightly different formulation. You don't have a quadratic objective function, you have a linear objective function. But your constraint is a bit more complicated. The constraint, it looks like it's a norm here. It's a 2 norm of a vector of a affine function that has to be smaller than an affine function. So this is what characterizes this cone. If you remember what we had with a cone, we had this set of points, you know, t and x, such that the norm of x is smaller than t, right? And that was creating for our second L2 norms, that was creating our nice ice cream cone, right? So this is the same formulation here. This is my vector, this is still a vector, and this is a linear relationship or affine. So this is what will define essentially my cone, and I have a linear relationship here, linear equality. Right? One important point is that this quantity, this is a norm, so this is actually not differentiable. So this is something that is quite different from this QCQP, where actually here we had something that is typically differentiable. Here we have something that is not necessarily differentiable because the norm is not differentiable, right? And it's different from QCQP because you don't have this square here, right? A QCQP would have typically a square there because the square of a norm, you can expand this, and this looks like you have some x squared plus linear part and plus some constant. Right? So we can show that this is actually a slightly more general form than this QCQP. If your C is equal to 0, if this right part here is equal to 0, then the SOCP will bow down QCQP. You can simply square this quantity and you end up with an equality that is similar to what we had before. If your AI here is equal to 0, this actually will be a linear relationship. This is linear, so actually this will become a linear program. And so this SOCP is viewed as a more general formulation than QCQP and LP. Right, so question is, why is this convex? And we know that already, why is this problem convex? For QCQP, we know it was clear. This one, why is this convex? And we said, well, this is actually a convex cone. But we could go into a slightly more detail, try to see why this is convex based on first principle. So the first thing you can say to say, well, this is a convex problem, is to say, well, I have here an affine relationship, and I take a norm over this. A norm is always convex, so actually this quantity will be convex. Here I have something that is affine. Affine is convex as well, is concave and convex. So I have a convex function plus an affine function. So I have a convex function plus a convex function. This is always convex. So that's clear, this quantity will be convex. The second approach you could do is say, well, let's go back to the definition of convexity, of convex function. And you can say, well, let's take now 2 points, x and y. And I take the segments between x and y, any points within this segment, right? And what I want to show is that I want to show the original definition that if this is my function, if I take 2 points, any points in between there will be smaller than actually the chord, right? That's what I want to show. How can you show that? You say, I plug into x, I plug this middle point here between x and y. And I do the same here. I take x, I take a point between x and y. So I'm looking at this function here, but evaluate at this point here. Right? Nothing special here. And now I'm distributing. And how can I distribute? I take this term here, a multiplied by x plus b here. I take this term here, a multiplied by I plus b there. So I break this relationship into 2 parts. And I do the same here. I have c multiplied by x here, and I have the y multiplied by c there. So you see that I have the theta here, the 1 minus theta, the theta, 1 minus theta. And then we use the triangular inequality. Let's say this quantity will be smaller than the norm of this, and this quantity will be, the sum of the norm of those sum is smaller than this norm here, and this norm there, and this term goes here, this term goes there. Bottom line, what you get is, again, what we have done before. You have here, this is your function, this function applied to point x. This is your function applied to point y. And then you weight those two. So this is essentially will gives you any points on this chord between those 2 points here. And this is larger than the function applied to any points in between, right? So again, what I was just writing is you have something like this. You take 2 points here. You take any points here in between, right? This point in between is essentially this one, theta x plus 1 minus theta y, right? So this is my x. This is the y. This is theta x plus 1 minus theta y, right? And I'm showing that these values of the function, the function evaluated at this point, is smaller than the value of the chord evaluated at the same point, right? That's why you have this inequality, and this is essentially the point here between this and that for a given value of theta. Okay, so that's the second approach here to show that this second order cone program is actually convex. We have linear objective function. We have an inequality constraint that relies on this norm, and so either you show it this way or you show it this way. Or the third one, you could argue, is to say, well, I can use the Hessian of that objective function. This is my constraint, and I could take a Hessian of this. Unfortunately, in this case, you cannot do it because this is not differentiable at 0, right? So you cannot actually compute your Hessian. Okay, so this is just so that we put this back into context so that you can see why this problem actually is a convex problem. Right, so now let's go back to our problem. Same problem as the one I explained you before. I have power minimization subject to SINR constraint or quality of service constraint, and we can find three solutions, three different ways to solve this problem. You either use SOCP, but you transform the problem, or you do a semi-definite program and particular relaxation. I will show you this later on. Or you do Lagrangian optimization based on KKT conditions. So we'll look at this next time. But let's look at this first transformation. And so this first transformation, what I do is the following. I take this term here. I bring this to the other side, right? Simply. That's all what I'm doing here. And so that's what I have. I have this term here, and I bring the other part to the other side. And then I'm adding this term here and there. So this is the same term. So if you cancel this and this, you get the same relationship as what you have in the previous slide. But the reason why we add this term here and there is because you can write things slightly differently now. So on this side, nothing special. You have this term plus these terms that gives you that. On the other side here, you have a term here that you can write in a matrix form. So you have here, this quantity is nothing else than the following. Hi multiplied by yi, hi multiplied by yj, and you do this for all possible j different than I, plus this one. So this would be the same as saying, I create now a matrix here, or a vector here, where I calculate the inner product between hi and each of those columns of W, right? And I will take a norm of this, norm square. So that will mean I will take the norm square of the first entry, of the second entry, of the third entry, and so on. So in other words, I will have this one plus this one. Okay, so this is just a different way of writing it. And then I have a sigma, and it should not be sigma squared, it should be just sigma here. No, it should be sigma squared. No, that's correct. So sigma squared plus so this term will actually contribute to this one. So here I create essentially a vector within this norm square. Okay? Nothing very fancy. I'm writing my objective function slightly differently. This one you're familiar with. I can write this differently. So I can say my W right? So my W is like I have W1 all the way to WK, right? And so if I have a sum of Wj squared, this is the same as saying I take W multiplied by WH, right? Because, or the opposite. So, and I take a trace of this. So what that means is that this is the same as taking trace of WHW. You can switch the order when you take the trace. And so if you have the diagonal entries of this are going to have W1HW1, W2HW2, all the way to WKHWK. Right? That's going to be the diagonal entries are going to have something off diagonal, and I take a trace of this, so I take the sum of all those entries. Okay, so this will be the same as this quantity. And now there is this nice property of a trace. A trace of a product of WH by W is actually a product of their vectorized form. So this is just, you know, a formulation. Vec, you remember what is vec? Vec is obtained by vectorizes this matrix. So I have a column here, a column there, column, column, and I stack all those vectors. So I take this one, I take W2, W3, W4, and so on. So I create a long vector, and I take the norm of this long vector. The norm of this long vector will actually be the same as taking the sum of the norm of each of those entries here. Right? It's actually quite intuitive. And this is why we have that. Okay, so now why people have done this is because now you have something like this that looks like a square smaller than something. And I have a vec here that will be also, we'll use this in the objective function. Now you will say, how is that related to SOCP? There is no SOCP yet here because you see you have a square there. It's not a norm, it's a norm square. And this is not just an affine function. This is actually a square of some affine or some linear function. This is clearly not what we're looking for when we have SOCP. But you can transform the problem in the following form. So let's go back to this problem. And I'm saying I want to minimize this quantity. So minimizing this quantity, I can say, well, I will replace this by another variable that we'll call tau, and say I want to minimize tau. And then I will bring this quantity into the constraint and say this quantity now has to be smaller than tau. So I'm manipulating the problem. It's not exactly the same optimization problem, but actually the solution will be exactly the same. So what I'm doing, I'm saying I have a minimization over a function f0 of x, and I'm subject to some constraints, right? And now what I'm doing now, I'm saying this is equivalent to saying I will minimize over another variable, tau, which is just scalar, and I'm saying my f0 of x will be smaller than tau. So I want to minimize a tau, but this f0 of x has to be smaller than tau. So by minimizing tau, I'm essentially minimizing an upper bound on the objective function, so I'm actually pushing the objective function down, right? So it's an equivalent formulation, equivalent in the sense that the solution to this problem will actually be the same solution as this problem, right? So this is what we do here. I'm taking this quantity, this is my f naught of x, and I will bring this as a new constraint by introducing a new variables. Here I have my tau, and I'm saying now my objective function, which was this one, or this one, I'm now minimizing it, and so this quantity has to be smaller than tau, right? And now I'm minimizing this quantity over this function, so actually tau is also actually an objective variable, so actually I need to optimize over tau as well. Actually, I should add this. Right, and so I have this. This was my objective function after transformation. And now I have this quantity. This was my original constraint that I have here. And I have rewritten here exactly the same. Okay, so this is something that we like because this is linear function. And this is a cone. This is what we have in the definition of the cone. Essentially, you have variables. You take second L2 norms, smaller than actually a constant or an affine function. Now, what is the problem left is this one. This is clearly not a cone, but what you can do is that you can do some transformation, and you can say, well, when you want to optimize your W, you always have some degrees of freedom. So this degree of freedom is the following. If I multiply W by just a constant phase, so if I multiply W by EWJ theta, I will not use theta because I've used theta before, but whatever, this. So if I multiply W by a constant phase like this, this will still be the optimal solution. It will not change. If W is an optimal solution, I can still multiply by this, will still be an optimal solution. Because if I multiply W here by a phasor, exponential J phi, this will be cancelled by the absolute value, right? So I have some degrees of freedom here. And this is interesting because you can say, well, I actually can choose this phase such that this term will always be positive. And so this is quite nice because then if this term is positive, then you can actually take a square root of this, you can cancel this, and you can cancel the absolute value. This term will be positive, and you can remove the square there. And by doing this, you have a term here that is now positive because you have assumed that you have these degrees of freedom in the W to make this term positive. And now you have not a norm square, but you have a norm. So you have a L2 norm. And this is exactly the same formulation as a convex cone. So you have a linear objective function. You have a second order cone here. And you have one here as well. So this is really the definition, the formulation of an SOCP. And so once you have that, and you will do this quite a bit in your coursework 3 and also in the problem class, you have now transformed the problem into a problem here that is actually convex. This is a convex problem, even though the original formulation here that we had here seems actually non-convex. The solution to that problem of non-convex problem is actually the same as this one here. But now we can solve this, and we can guarantee that there is one global optimal solution, right? So how we solve this, we will not go into this in this module because definitely I don't have time. But there are many softwares that exist, and one of them I will use is called CVX. It's a software that is used for convex optimization. And you can write a code in a specific form into this software. And I will go into this next time, show you how you can write this. But this is something you're going to have to do quite a bit in coursework 3. Okay, so sorry, I will have to stop now. And I see you in 3 weeks from now. In the meantime, you will see Yang and probably a bit of Hongyu as well. Right. Okay, thank you.